that's for scalar. How about vector? If Z is Z1, Z2, blah, blah, Zn transpose, okay, it's a column vector, okay. It's a vector in Cn, so it consists of complex numbers. The length of Z is given by, okay, is Z1 squared plus Z2 squared, blah, 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 plus Zn squared, okay, the sum of this, and then square root, okay. If you write it, okay, in, like we did like earlier, it's going to be Z1 conjugate times Z1 plus Z2 conjugate times Z2 plus Zn conjugate times Zn. Because this one, Zi conjugate times Zi is like a square of Zi, right? Square of length of Zi. Okay, so this one, okay, and square root. Or put it another way, okay, if you try to denote like this one as like an inner product, okay, then it's going to be Z conjugate, okay, transpose inner product times Z, okay, and the square root. Okay, so here, because of this, we define, okay, the Z conjugate transpose as ZH. Okay, this H stands for Hermitian. Okay, so remember the Hermitian of vector Z is its conjugate and transpose. Okay, it's conjugate and transpose. If we define like that, then the length of a vector Z, okay, complex with complex numbers is going to be ZHZ, okay, square root. So it's because of this what should I say, because of this reason, okay, we can see that we define the conjugate of a vector Z to be the transpose, the conjugate and the transpose, okay, of Z. So with that in mind, once we define that, okay, we call that as a complex inner product. Okay, the B be a vector space over the complex numbers. An inner product on B is operation that assigns to each pair of vectors Z and W be a complex number Z W. Satisfy the following condition. Okay, first Z. Okay, Z inner product Z is 0. If only Z is 0. Okay, and for all Z and W be okay. First Z inner product Z greater or equal to 0. Okay, Z inner product W is going to be the same as W inner product Z, and alpha Z plus beta W inner product U is going to be alpha ZU Z inner product U plus beta W inner product U. Okay, so we have these two rules. Then we can derive some other stuff. For example, we want to prove U inner product alpha Z plus beta W is going to be this. I mean here, okay, be careful. It's a conjugate of alpha times U inner product Z plus conjugate of beta times U inner product W. Okay, so this we have conjugate here. Okay, whenever something appear in the later term, so how do we prove that? First, when you change the order, like in this conflict, I think when I mentioned it, I mentioned it, right? So first, this one, U alpha Z plus beta W. Okay, because like a distributive law can only be used when like when that sum okay appear in front. So we need to change the order. So it's going to be conjugate. Okay, alpha Z plus beta W, and then you, according to that, okay, this, and then okay, with that, okay, we can use this rule to get our stuff. So it's going to be conjugate. Okay, inside here we have like alpha ZU plus beta WU. Okay, but here, I mean, it's UZ, UW, so the order here is wrong. So how we do? First we get rid of the parentheses, so it's going to be alpha conjugate Z U conjugate plus beta conjugate W U conjugate. So we need to change the order of the ZU and the WU. So what happens is we apply the first rule, the second rule again. So it's from the previous rules. So of course, you can, there are other rules you can derive. Okay. I think I gave, I will give you some practice questions, like including some of the other rules you can derive. Okay. And now that define ZW equal to WHZ. Okay, be very careful. Okay, ZW is WHZ, not ZHW. Okay, for all ZW is C to the power n. Okay, so we call that as the inner product for CN. Okay, so if Z is this one, W is this one, then Z inner product W is WHZ, right? So WHZ, so first you get the conjugate, and then use a transpose. So it's going to be 2 minus I, negative 2 minus 3I, and times this one. Okay, this is W, sorry, Z, that's Z. And then the result is this one. Okay. Here, okay, if this inner product is 0, actually it implies that, okay, they are these two vectors, or these two, the complex vectors are, orthogonal. Okay, we will define that shortly. And the ZZ is ZHZ. Okay, it's going to be, basically, this one times this one, so it's going to be this one plus this one is going to be 36. Okay, so if you want to get like the length of Z, it's actually 6, because the square root of this Z inner product Z, and WW, okay, W inner product W is WHW. If you do this calculation, it's going to be 18. So this is pretty straightforward. So conjugate and the permission, okay, and now we are extending the idea from the vectors to matrices. Okay, so M is an N by N matrix with Mij equal to Aij plus Ibij, which I and J. Okay, so as you can see that, like each element in the matrix is a complex number. Okay, obviously you can write, M equal to, A plus IB. Okay, basically like a separate elements into like a real part and an imaginary part. Okay, then the conjugate of M, okay, denoted by M bar is A minus IB. Okay, so this conjugate idea is similar to vector, is similar to scalar. Okay, basically, if it's like A plus IB, the conjugate is A minus IB, it's straightforward. And MH, again, as I said, it's the conjugate and then transpose. So it's transpose of M bar. Okay, so if A, B are like a C N by N matrices, and the C is N times R matrix, then A Hermitian, and then Hermitian again is A itself. And alpha A plus beta B Hermitians, A is alpha conjugate times A Hermitian plus beta conjugate times B Hermitian. And AC Hermitian is going to be C Hermitian, A Hermitian. I mean, this, it's not the definition. Okay, here, these are these are the rules you need to prove. Okay, I would just give like one. Okay, the other I think you can do it yourself. Okay. So, for example, A Hermitian is A. So, we know like A so A is AIJ, right? Okay, what is A Hermitian? A Hermitian, okay, it's going to be first the AJI Hermitian, right? Like because it's transpose, so IJ will get exchange, and then A Hermitian obviously is going to be we change this IJ again, and then this one is going to be okay. So this is A. Okay, and the others, I think you can do it yourself. Pretty straightforward, but they are not definition. I mean, you need to prove, you show that it is the case. Okay. Okay, let me do one more. Okay, just the second one. So alpha A plus beta B Hermitian. So it's going to be alpha. So it will be alpha A plus beta B Hermitian. So what is alpha A plus beta B? It is if you look at like the IJ, the AIJ, so alpha times AIJ, okay, plus beta times BIJ, okay, this one, okay, and then Hermitian. So it's going to be conjugate and then transpose, right? So it's going to be conjugate. So alpha bar and A ij, I mean, because it's transpose, so it becomes ji plus beta bar. Same thing. It's b ij becomes ji and the Hermitian the conjugate. So it's like that. So then this one alpha bar stays like that. This one is a Hermitian according to the definition. Okay, and this one same thing, beta bar. This bji Hermitian is b Hermitian. So that is why we have that. Okay. So matrix N is said to be Hermitian if N equal to NH. It's an interesting stuff, okay? It is interesting stuff. So Hermitian is a property. For example, if M is like that, you see, the diagonal are real, and